Looking at this picture, if h is 10 feet, what's the velocity at the exit? So we're going to once again apply Bernoulli's equation. I've already written down the assumptions because I had started to record this video and my dog started losing her mind and barking, and I was just too lazy to rewrite it. So let's talk about those assumptions really quickly. We've got the streamline. We're going to draw a streamline in, so we're going to assume that we have one. Steady flow. There's absolutely nothing in the problem that says the flow is dependent on time, so we can assume steady. We're going to assume an inviscid flow. Once again, we're not going to assume there's no friction within the system, and we're also going to assume that density is constant. We're going to assume it's a liquid, so it's generally incompressible. So now what we need to do is we need to draw a streamline to calculate what is going on. Now there's a couple different places that we can do this, but basically all those particles in the tank, there's going to be some line that's going to take it to the exit. So we just need to pick one of these particles. Generally, when we're dealing with a large tank, you usually want to pick the surface of the tank. Why are we picking the surface of the tank? Well, usually we know what the pressure is. In this case, it's going to be atmospheric. But more importantly, we know what the velocity is. Because the velocity is generally considered to be zero. Yes, it is draining, so it will be have a little bit of velocity going in the downward direction. But it's generally quite small, as long as the hole is small compared to the tank. So if we do that, what do we know? Well, let's draw that streamline in, and we're just going to say that this point right here, there's some fluid particle, and we're going to take it right there, 0.2, and it's going to go, that's generally the path that it's going to take. So there's my streamline of where it goes from 0.1 to 0.2. Now I have 0.2 picked just barely on the outside of the tank. Now the reason for that is once I get outside of the tank, it's no longer constrained by the tank, so the pressure will be atmospheric. If I picked it just on the inside of the tank, I'd have to worry about hydrostatic pressure, and I really don't want to do that because then I'd have to calculate it out. Now that I've picked it just barely on the outside of the tank, well, that tells me that pressure 1 and pressure 2 are going to be the same because they're both exposed to atmosphere. So I know that, let's write it as delta z, the change in the height is going to be 10 feet. So what we can do is we can say that z2 is 0, and then z1 then would be 10 feet. You could have z1 being 0 and then z2 being negative 10 feet, and it's all going to work out. That's all fine. We also know that v1 will be 0 because of the surface of the large tank. Now, let us write Bernoulli's equation between those 2 points. Pressure 1 plus gamma over 2 velocity 1 squared plus gamma z1 is going to be equal to pressure 2 plus density over 2 v2 squared plus gamma over z2. Now typically you'll see, and especially when we get to the energy equation, I'm always writing these full equations out and then canceling out the terms to make things easy. So P1 is equal to P2. So P1 equal to P2. So those fall out. V1 is 0. Z1 is 0. So there we go. Our equation knocks down pretty quickly to just this little part over here. So let's rewrite that. I'm going to isolate out my velocity. And so the way I'll do that is I will move everything to the other side. And I just noticed as I was moving that to the other side, I crossed out Z1 instead of Z2 being 0. So let's roll that back. It's a little bit easier for me since I can just erase it digitally. So there we go. Now because we're looking for Z1. So I'm going to move over. I'm going to multiply through by that row over 2, and then I'm going to take the square root of everything. And so what that's going to give me is the velocity at 2 is going to be equal to 2 times height, so Z1, times G, because when I take density, specific weight divided by density, all that's going to be left is G, and then I'm going to take the square root of it. Now this is actually a pretty famous fluid mechanics equation. This is what's called the velocity of a free jet, which just means that you poke a hole in the side of a pot or a bucket, and this will be the equation. So now if we plug our numbers in, 2 times 10 feet times gravity, which is 32.2 feet per second squared. You're going to end up getting feet squared per second squared. You take the square root of that. That's going to be feet per second. Great. That's the units we expect. So V2, if we calculate that out, is going to work out to be 25 feet per second.